Hello and welcome to Lesson 4 of Unit 2. This is Derivative Rules Part 2. Today we're going to be talking about applying the exponential and logarithmic function rules and the product rule. Okay, so we're going to start with the product rule. I'm going to do a quick derivation of the product rule because I think it's kind of cool. It's not something that we need to know. Ultimately, the rule at the end is what we need to know. But I do like to do the derivations of the product rule, and like we did in the previous lesson with the power rule, and like we'll probably do in the future with the quotient rule. So let's go ahead and apply the definition of derivative to capital F of x, which we defined as the product of the function f and g. Okay. So plugging in x plus h to the function f times g. And then here's the tricky part. And what you'll see this year in calculus is that a lot of these derivations or a lot of the proofs that we'll do involve one or two kind of tricks. And that's the reason why I like to do these derivations, because ultimately it's not important for the AP exam to know the derivation, but for somebody like you who might want to be studying mathematics later, knowing these tricks exist and are used throughout mathematics is what's going to make you a better mathematician. So what we're doing here is in red and in green, we're adding and subtracting the same thing. So ultimately, we're adding 0. But we're adding these products because we need the pieces of them to create our ultimate end result. Okay. So now we've done some factoring. In the first two terms factored out. Let me see if I can point that out here. F of x plus h and f of x plus h have been factored out, leaving g of x plus h minus g of x. And in the second group of terms, the g of x has been factored out, leaving f of x plus h minus f of x. So maybe you can see where this is going now, especially those of you who know what the product rule is. We'll use our limit rules to divide this into the sum of two separate limits. All right. And then in the first limit, since h is going to 0, this factor ultimately is just f of x. And so it can come out. This factor, g of x, isn't affected by the limiting value of h, so it can come out. And I'm left with two new definitions of derivative, one for g and one for f, which leaves me with f times the derivative of g plus g times the derivative of f. And that is our product rule. So given a function that is the product of two functions, the derivative of the function itself is oftentimes referred to as the first times the derivative of the second plus the second times the derivative of the first. That's a lot of times how the product rule is read or said, especially in the process of doing it. Okay. So now we're going to take a look at the derivatives of e to the x and natural log of x. So I thought it might be fun to look at where the derivative of e to the x comes from, because the rule is really simple. But why the rule is what it is, isn't. So again, the derivation of this rule isn't necessarily required for the course, but the thought process and the thinking and the mathematics behind it is the type of mathematics that will make you a better mathematician by being exposed to it. So let's first take a function, and that function is not e to the x, it's some exponential function b to the x. We don't know what the base of the exponential function is. We'll apply the definition of derivative, and then through some exponent rules, we can factor out a b to the x. All right. Now, because the b to the x isn't being affected by the limiting value of h, b to the x can come to the front of the limit. And what we're left with here is what looks like a definition of derivative for some function evaluated at e, not just some function, but for f of x evaluated at 0. So ultimately, what we have is that the derivative of an exponential function with base b is itself here times the derivative of that function evaluated at 0. So what we'd like to do is examine the special case where that derivative is equal to 1. So we can apply some algebra here. Multiply by h. Of course, the limit follows the h. Add 1 to both sides, and then raise both sides to the power of 1 over h. So we end up with b being equal to the limit as h approaches 0 of 1 plus h to the power of 1 over h. Now this limit might look somewhat familiar because we explored a very similar limit, or a limit that looked sort of the same, except it was the limit as x approaches infinity, and it was 1 plus 1 over x to the power of x. And that limit was in the activity where we explored limits at infinity, and that limit we decided was evaluated to e. And so is this one. This is yet another definition of e. So what we get here is that the exponential function, b to the x, whose derivative is itself times 1, is the exponential function where the base is e. Okay? So, the derivative of e to the x is just itself. And that's one of the characteristics of the function e to the x that makes it such a powerful function for higher level mathematics, especially in differential equations. And then we're not going to do the derivation for the natural log of x, but the derivative of natural log of x is just 1 over x. Let's look at an example. So we have a table of values, okay? We have x being equal to 2, f of x is 7 when x is 2, f prime is negative 2, g is negative 5, and g prime is 3. And we're being asked here to evaluate the function h of x, which is defined in terms of f and g, okay? There's a product going on here, right? And we want to find the derivative of h at 2. Okay. So because we have a product, we're going to apply the product rule. So we have to find our first and our second. So our first is the first function in the product, and the second is the second function in the product. And then applying our rule, we have the first times the derivative of the second, which in this case is just g prime, since the derivative of a constant is 0, plus the second times the derivative of the first. And here we have two other rules that are coming into play: the derivative of a constant being 0, and the fact that a constant times a function is just the constant times the derivative of the function. Okay, and then all we're doing is plugging in 2, writing out the values that those are associated with, and we ultimately get 18 as our answer. Okay. So for our second example, let's look at two functions, f of x and g of x. Let's evaluate f of x first. So f of x is a product. It's x squared times e to the x. So the first and foremost important thing about differentiating functions is being able to determine what rule needs to apply. And anytime I see a product of functions, anytime I see one thing times another, I'm going to be using the product rule. So here we have our first, which is x squared, times the derivative of the second, which is just e to the x, plus the second, e to the x, times the derivative of the first, which is 2x by the power rule. And then we simplify. Oops. The second part here, x times natural log of x. So first, we do first times derivative of the second. Remember, we said that the derivative of natural log of x is 1 over x, plus the second times the derivative of the first being x, so its derivative is just 1, and then simplify. So in summary, follow the rules and everything will be okay. So we have the derivative rules for e to the x and natural log of x, and the product rule. See you in the next lesson.